All right. So load 4D. You're loading 4 elements into, it looks like Rx. And you're going to load, you're going to multiply A, which is in F0. Are you loading them in there? Yeah, you multiply them. Then you're going to load Y, multiply, or you're adding. You should be adding. Right, you're going to add everything from Y, and then you're going to store them back out. Okay. Increment X and Y. Notice here they're jumping down 32. Oh, 32.
That's the length of the words.
Yeah, word align, yep. Right, that makes 32 bytes. Okay. Compute the bound. Oh, just make sure we haven't gone past the bound of probably 512. Yeah. Make sure we haven't gone past 512. Is that what it looks like? R4. Where's R20 coming? Did they ever define R20? So I guess R20 is the bound. They just never tell you that. So you make sure the bound hasn't happened, and then check if done. So there, hopefully you can see that it's able to do 4 of these at once, as opposed to only 1, and that does save you some work. Or a lot, actually. Oh yeah, the roofline performance. Where is your picture? There we go. Okay. So roofline performance. The question is, how do we measure the performance of these instructions? Well, this is big O down here, but how would we do the performance of these? Want to plot the peak floating point throughput as a function of arithmetic intensity. So it ties floating point performance and memory performance together for a target machine. Why do we want to be doing this?
To crunch the numbers fast.
Why are we tying together floating point performance and memory performance?
Because that's the overall performance.
That's all right. It's the overall performance, sure. Well, okay, let's put it this way. If we had a terrible memory system, but many floating point operations, what type of programs would run well on our machine?
Small memory.
Small memory, right. Small memory. No, that's right. Small memory ones. If it was the other way around, what programs would run well?
Small calculations.
Small calculations, or with large memory. Yeah, you got it. So the point here is to show that it's not just a simple benchmark anymore. Now that you're in SIMD and memory is such a bottleneck, you need to make sure that your memory system can handle loading and storing all this memory, as well as being able to calculate the performance. You'll see where I'm going with that? The way we calculate what it's, we usually base the calculation on what we call arithmetic intensity, namely how many floating point operations are there per average instruction. So on average, how many times are you doing a floating instruction per every memory instruction? Sorry, let me make that clear. Or per byte read. So they're doing it per byte read, which is fine. So down here, there is one memory instruction, one floating point instruction for every 8 bytes read. Is that what it's saying? Yeah. And then right here we have one floating point instruction for every 1 byte read. Over here we have 16 floating point instructions for every 1 byte read. So
what's that vertical axis? Double.
Oh, this guy right here?
Double precision.
So this is double precision gigaflops per second. So how much work was it able to get done? How much work was it able to get done? And down here is what's the arithmetic intensity of the program? So what are these two things telling you? Let's start with something easy. Once it flatlines right here, and it can't get past 102.4 gigaflops, what does that mean?
Your memory sucks.
Yeah, I think you got it backwards. Remember, this is...
Memory is no longer an issue.
Yeah, memory is no longer an issue because this is number of floating point instructions per byte. So 1 floating point instruction per 8 bytes read. This is 8 floating points instructions for every byte read. So over here, you're having very few memory instructions compared relative to the number of floating point instructions. So what's saying right here is you're able to fully utilize all of your floating point units, and you're basically just waiting for your floating point units to complete. When you're on this curve, what does that mean? Or I should not say this. Well, I can call it a curve. This linear slope. How about that?
That's the effectiveness of the calculations, or how well they are.
How well they are. So over here we're saying gigaflops. That's all your floating point units are being fully utilized. We just can't get any more performance out. And that's when we have, let's say, 8 floating point operations per byte read. But we're saying here when you're doing 1 floating point for every 8 bytes read,
So
it
that's
drops.
the memory performance.
So that's this is the memory performance bound on these two sides. Yep. All right. Hopefully, well, which one of these two looks like a larger processor just by the numbers?
The NEC.
Yeah, the neck. Yeah, that was a supercomputer one. But your i7 is more of a desktop one. Which one do you think has a better relative memory system? Let's put it that way. And then why?
Yeah, the NEC.
And why is that?
Well, the slope ends sooner.
Right, so it's able to obtain its peak performance even with a fewer, floating point instructions per byte read. Right. Basically, this point where it shifts from this linear slope to a flat line, the further left it is, the better your memory system is. The further right it is, maybe you have too many floating point units. Maybe you should work on your memory system. Okay. Any questions about these graphs? Because you'll probably see them again. Hint, hint. Okay. So now we've talked about that. Last thing are your GPUs. When you have, hopefully y'all are familiar with these. Matt, you've never seen these before, have you? Is this just too old? It is, with the old Voodoo cards that came out. All right. Given the hardware investing to do graphics well, how can we supplement to improve performance of a wide range of applications? This is actually pretty cool. Keep in mind that we have a heterogeneous execution model. The CPU is the host, the GPU is the device. The GPU, from everything I've read so far, does not run any standard operating system. So you can't just drop Linux on the GPU. So Linux, your OS, has to run the CPU, but that doesn't mean it can't take advantage of the GPU's architecture in order to accelerate certain, routines. Actually, isn't there a graphics card shortage right now? Why is that? Do you know why?
Just the monopoly money.
Monopoly money. No,
I don't get it.
he's just being
Oh,
he's being Matt right now. So right now there's a lot of people are using it for trying to crack hashes.
oh, yeah, I heard
Not-
they,
Yeah,
the GPU calculates it faster than the CPU.
way faster. Like not just twice as fast, more like hundreds of times faster.
That's because it is a multiple.
It's because it's essentially a vector SIMD machine. Everything we've talked about in one. And when you're doing hashes, you're basically guessing a bunch of hashes at the same time, and each one of those is basically their own routine. So you just shift all of those over, or shift all those over to the GPU, let it crunch the numbers, and see what comes back. So you're just able to do not a million, but many of them at once, as opposed to one at a time. So people have a C-like programming languages for the GPU. Unifies all GPU parallelism as what they call CUDA threads. These slides are going to go through NVIDIA's version of it, which is with CUDA. There's something nowadays we use called OpenCL. Just remember that NVIDIA or CUDA is basically proprietary to NVIDIA. OpenCL can run on basically any chip. But the idea is you have single instruction, multiple thread. And this is a little different because they're starting to go into what we call thread parallelism, but not quite. We're not quite to that level yet. Really what's going on is they're taking this idea that you have an instruction, you're able to operate on multiple pieces of data, and you're just going to extend it so that you can have multiple of these SIMD instructions going at once, but you're going to be restricted on other instructions that you can execute. So each thread organized to a block organized to a grid. All right, so there's a hierarchy going on right now. Is the main thing to keep in mind. The hardware is going to handle the thread management. The OS basically sends it all of it, and the GPU takes it from there. Similar to vector machines, works well with any data level problem, any type of scatter, gather, mask, or large register files. I hope you're doing scatter and gather in OS. If not, hopefully you'll do that soon. Let's see, no scalar processor, uses multi-threading to hide memory latency, has many functional units as opposed to a few. The big problem here is you can't do interrupts or exceptions because it's a GPU. So multiply two vectors of length 8,192. All right, code works for all elements in the grid. Thread blocks break this down to manageable pieces, so you have 512 threads per block. Each instruction can execute 32 at the time. So the grid size is 16. Why is the grid size 16? What's that? 512 over 32. Yeah, okay. All right. Wow. This makes way more sense with a picture. Oh, where's the silly picture?
That's not the picture.
No, that's a picture.
It's not the picture.
I don't know if I like this picture. That's it? Oh, man.
So
Let's learn this off of Wikipedia. Oh, man. All right. So lastly, with GPUs, we're not going to do any GPU programming in this course. Although maybe I should have made you do that.
replace the second project with it.
I'll consider that for next time.
Swap next class period. Get back to us.
Okay. So you've broken up the large instructions. Well, I guess we do need to look at the code. Where's the code?
I don't think they gave us code.
What?
Oh, never mind.
Yeah, it's right here. So block ID times 9, the block size 512.
So weird.
All right, this
The
doesn't.
question was, why was the block size 16?
Yeah. Okay, let's go back to that then. I tried to skip ahead to make this easy and I made it worse. All right. 17 instructions execute 32 at a time. thus the grid size is 16.
It's-
Grid size is 16. 16 blocks. Well, you need 512. What was that? What is that? That's 4. Hold on. 12, 13. Right. Yeah, that makes sense because you have 5 threads per block. So for each, because if you do, what is it, 8,192 divided by 512, you get 16 blocks. All right, good. Block, stripe, mine, vector loop. Well, that's funny. A block. Just think of it as being able to execute all these threads in parallel, or maybe only some of them. You've grouped them in together. Block is assigned to a multi-threaded SIMD processor by the thread block scheduler. Current generation, and by current they mean by 2012 because it's wider. Whew. They really need to not write current generation when they're making computer science. It just does not work. Because you remember the Fermi architecture, right? Yeah. Yeah. Whew. All right, so each thread has its own program counter. Thread scheduler uses scoreboard to dispatch. Hey, okay. Would you prefer the
Tomato soup.
can't even say it straight anymore. Method?
Yes.
Hey, but why do they not use the tomato soup method?
Because it's copyright and data dependencies.
There are no data dependencies. That's why. That's the advantage that GPUs take advantage of, is the fact that you don't have data dependencies between threads. So it doesn't have to do any checks. Let's see. Keeps track of 84 or 48 threads. Wow, that was dyslexia. Of SIMD instructions to hide memory bandwidth. Okay. Thread block schedulers blocks to the processors, which within each processor you have 32 SIMD lanes, wide and shallow comparing. All right. There's a hierarchy, and you just keep drilling down until you finally start executing things. But get the idea. There's 32 SIMD lanes.
And there's no data dependencies because they're working kind of like with vectors, so.
Right. You have
One
to,
doesn't-
when you use a GPU, you're basically telling the GPU there's no data dependencies, just crunch these numbers. So what is this? 1, 2, 3, 4, 5, 6, 7, 8. So that's 16, another 16. That's a SIMD lane. Notice that each lane, which is going to execute one of the threads we've talked about, has its dispatch where it can do a floating point or integer unit, and then its result queue. So notice that there's many of these. Nowadays there's even more. And then you can also load store into each of these. That's some type of floating point unit, or what is S? I don't know what SFU is in this one. But yeah, it's basically wide range, huge register file with the dispatcher up top, and then almost like a small one cache. But it's a uniform cache to then spit it back. So it's really just a wide number crunching machine. It doesn't have anything to take care of data hazards or branch hazards because there are no branches. Doesn't that make it easy? All right. Is there anything else we really need to talk about here?
So when they're talking about 512 threads, I assume those threads are fairly simple.
Yeah, by a thread. That's why it's not, I wouldn't call it thread level or process level parallelism, because a thread is really just execute a couple of instructions, spit it out. You're not doing last I did this, you weren't doing loops.
Just
And
add, multiply.
Right. And that gets rid of any data hazards and any control hazards, so you don't have to do branch prediction or anything like that.
Ah, there you go.
Hmm?
There you go.
There you go. Right. So you're really just pushing what these GPUs are. You're just pushing numbers through and it's just crunching it out as fast as possible. And for these trying to crack hashes, that makes sense because you're usually just trying multiple different hashes at the same time. Let me not do that again. Okay. All right. It's really all that matters here. Okay, one last thing. Loop level parallelism. Whew, that was bad. Determining whether data accesses in later iterations are dependent on data values produced in earlier. Correct.
No.
So, looped carry dependence. Whether data accesses in later iterations are dependent. It is not. So why is there no loop carry dependence here? If you were to unroll this loop, what would it be?
Just looking at a strict array, huh?
Yeah.
Because
Doesn't matter if these two are swapped.
No.
No. So you can execute all of these in parallel, right? So what a compiler can do, if it knows about these SIMD or vector machines, is once it identifies this type of situation, it can just package these all up and send them to the GPU and get them back and be able to execute all this at the same time. Notice that also requires that these values up here are constant. And of course, just realize it's actually 999, 999, 998, 998, et cetera, et cetera.
and each one will be a thread.
Yes.
So
And this could be thousands.
999.
Yeah, exactly. And you just ship it out, and then when it comes back, it's done. Swell. All right, so that's data dependent. We're not going to get too much more into that for computer architecture, at least not right. And at least not for this class. Let me go ahead and close the slides. Let me jump back